this video lecture, we are going to see section 3.2 of chapter 3, which is having the heading Increasing and Decreasing Functions. In this lecture, we'll define what increasing and decreasing functions are and see some examples related to it. So you can see in the box that the sign of the derivative of the function indicates whether a function is increasing or decreasing. That's our aim of this section. So we'll look onto it as we move forward. We just keep that in mind. So how to understand whether a function is increasing or decreasing? This is a basic aim. So we show that a function is increasing when its derivative is positive and a function is decreasing when its derivative is negative. That's what we are going to deal with. Okay, so you can look at this example you're seeing here in the figure, and you have x0 here, x1 here, x2 here, x3 here. Correspondingly, x0 will have the functional value here, right? This is f of x0. This will be f of x1. This will be f of x2. And this point will be f of x3. So you can see that at this x0, if we are drawing a line, a horizontal line parallel to the x-axis like this, the function is cutting it here and then it is moving up, right? Below this line, the function is like this and it is moving up. That means here the function is increasing at x0, okay? And consider the point x1, okay? Here, if you are drawing a horizontal line parallel to the x-axis, here nothing is happening. Like the function is going like that and like this. Like it is not going up like, from here. It is going down. So here we can say that a function is neither increasing nor decreasing at the point x1, at this point. And consider the point x2 and see the function. We are drawing a horizontal line parallel to the x-axis here, and you can see that the function came like this and then the function is again going down. That means the function is decreasing at the point x0, and at the point x3 it is the same behavior which is seen earlier at the point x1. That means here it seems to be like that, but it is not, because here the function is going like this and then the function is going up. That means the function is increasing at x3. So that's how we can observe or infer from this figure which is given. And to have some simple examples, suppose if our function is this is a function, okay, this is our domain and this is our range, right? So this function, take any point. You're taking a point here, the function is increasing there. If you're taking a point here, the function is increasing there, like that. That is for any x1 and x2 such that x1 is less than or equal to x2. Here f of x1 will be less than or equal to f of x2. This is an important property of an increasing function. So suppose if our x1 is here and x2 is here, you know that the corresponding value of the function will be f of x1 here, and similarly the value of f of x2 will be here, right? This will be f of x2. That's what the definition says. That is, if x1 is less than or equal to x2, that will definitely mean f of x1 is less than or equal to f of x2. Okay. So the next diagram you can see, and the function here you can see that the function is decreasing at every point, right? So here see if x1 is less than or equal to x2, so take x1 here and x2 here. Okay, we are drawing the corresponding values of the function and those points. See, this will be f of x1 and this will be f of x2. See here you can see that x1 is less than or equal to x2, but f of x1 is greater than or equal to f of x2. So this is the characterization of a decreasing function, because the function is decreasing everywhere in the domain. Here the function is increasing everywhere in the domain. That's why it's called increasing function. Here it's called decreasing function. And for this function, we can say that all the points to the left of this function till here, right? They are forming, uh, or at those points we can say that the function is decreasing. And similarly, all the points to the right of this function, we can say that the function is increasing at all those points. And the points here, we can say that the function is neither increasing nor decreasing. So to the left, we know that the f is to the left, we know that f is decreasing at all the points, and to the right you have f is increasing, and in between you can say that f is neither increasing nor decreasing. So to look on into the next areas, we are going to rigorously define an increasing function at the point x0. So if there exists an interval, open interval AB containing x0 such that a strictly less than x strictly less than x0 will imply f of x strictly less than f of x0, and x0 strictly less than x strictly less than b will imply f of x is strictly greater than f of x0. That is, f of x0 is strictly less than f of x. That will mean that the function is increasing at x0. And similarly, if f is decreasing at x0, if there exists an interval, open interval AB containing x0 such that if a is strictly less than x strictly less than x0, then f of x is strictly greater than f of x0. That is, f of x0 is strictly greater than f of x. If x0 strictly less than x strictly less than b, then f of x is strictly less than f of x0. That is, f of x0 is strictly greater than f of x. Then these both of them will imply that f is decreasing at x0. So here you can see we have underlined x strictly less than x0 will imply f of x strictly less than f of x0. Here also x0 strictly less than x will imply f of x0 strictly less than f of x. So that is the property of increasing function. And here if x is strictly less than x0, then f of x0 is strictly greater than f of x. And also here x naught strictly less than x will imply f of x naught is strictly greater than f of x. So that is the property of decreasing function, and we can see the first example. So the first example asks us to find or show that f of x is equal to x square is increasing at x naught is equal to 2. So for that, from the definition, we have to find an open interval in which 2 is present. So we are taking the open interval to be 2 belongs to open interval 1, 3. Okay, and we are partitioning it into two parts. The first part we take 1 strictly less than x strictly less than 2, that will imply 1 square strictly less than x square strictly less than 2 square, that is 1 strictly less than x square strictly less than 4, and you get to know that x strictly less than x 2, here we have f of x strictly less than f of 2, that will imply the increasing property. Here 2 strictly less than x strictly less than 3 will imply 4 strictly less than x square strictly less than 9, that also implies the increasing property of the function. So that will imply that the function is increasing at 2, uh, right? Because to the left of 2 and to the right of 2, you are getting that the function is increasing. And there are two other special factors which we have to note, that if f of x naught is equal to 0, if f is increasing at such an x naught, we say that f changes sign from negative to positive at this x naught. So here you can see a figure here. See, f of x naught is equal to 0 means if the function f is meeting the x-axis at some point x naught. So here this is the x naught, and we have the function like this. So you have when we have a point to the left of x naught, the corresponding functional points will be negative, and if you have some points to the right of x naught, the corresponding functional points will be positive. So definitely when we are moving from the left to right, you are getting that the function is increasing, or we can say that the function is taking negative values first and then it is taking positive values. So we say that f changes sign from negative to positive at x naught. And similarly, if f of x naught is equal to 0, this is an increasing function. Suppose if it is a decreasing function, see, you can see here. So that will mean to the left of x naught, the function will have positive values, and to the right of x naught, the corresponding functional values will have negative. That means we say that f changes sign from positive to negative at x naught, that is for a decreasing function. And you can verify the change in sign for this graph. Here you have this x1, so the function changes from positive to negative at x1, the function changes from negative to positive at x2, the function changes from positive to negative at x3, the function changes from negative to positive at x4, the function does not change at x5 because it is having positive, and again it remains positive, right? And at x6 the function is changing from positive to negative. So that's the observation we get from the figure 3.2.4. Now you have example 2, which asks us to ask us where does f of x is equal to 3x minus 5 change sign. So for that you have three steps. The first step is suppose f of x naught is equal to 0, find x naught. So f of x naught is equal to 0 will imply 3x naught minus 5 is equal to 0. Consequently, x naught is equal to 5 by 3. Now to look to the left of 5 by 3 and to the right of 5 by 3. When x naught is strictly less than 5 by 3, we have 3x naught minus 5. Just cross multiply and take this 5 to the left. That will be strictly less than 0, and this is nothing but f of x naught. And if x naught is strictly greater than 5 by 3, that will mean 3x naught minus 5 is strictly greater than 0. So that means at this point, x naught is equal to 5 by 3. The function is changing from negative value to positive value. So that's how it changes sign from negative to positive. Now, for example 3, the same manner, you have to check where the function f of x is equal to x square minus 5x plus 6 is changing sign. For that, first assume that f of x naught is equal to 0. Then you have x naught square minus 5x naught plus 6 is equal to 0. It is a quadratic equation, so you have product to be plus 6, sum to be minus 5, so you have minus 2 and minus 3, because when you multiply them you get 6 and when you add them you get minus 5. And you can factorize the same quadratic equation as x naught minus 2 into x naught minus 3 is equal to 0, their product. So you have x naught is equal to 2 and x naught is equal to 3. So you have to check for the same criteria which we saw in example 2. You have two cases here. So you have to check for x naught strictly less than 2, x naught strictly greater than 2, then x naught strictly less than 3, and x naught strictly greater than 3. So that's the cases. So for that, x naught strictly less than 2, just for our convenience, I'm taking x naught is equal to 1 to find it, because it is a complicated function, right? So if x naught is equal to 1, you calculate the function at x naught is equal to 1. So you get that is equal to 2, which is strictly greater than 0. And for x naught strictly greater than 2, suppose take x naught is equal to 2.5, because you already have 3. So take something which is less than 3. So you take 2.5. Using your calculator, when you find, you get that to be equal to minus 0.25, which is strictly less than 0. So you have positive here, positive here, negative here. That means f is changing from positive to negative at x naught is equal to 2. Similarly, for x naught strictly less than 3, take x naught is equal to 2.5. We already calculated it is negative 0.25, which is strictly less than 0. And if x naught is strictly greater than 3, suppose take x naught is equal to 4, then calculating you get that is equal to 2, which is strictly greater than 0. That means f is changing from the negative to the positive at x naught is equal to 3. So that's how we observe and conclude example 3. And also we had learned that a linear function is of the form mx plus b. Y is equal to mx plus b. This y is simply called L of x. You can call it y. This function, linear function, is increasing everywhere whenever the slope is positive. Slope should be positive for the linear function to increase. So if we have a function f of x, the corresponding linear approximation which we learned in earlier section is that f of x is equal to f of x naught plus f dash of x naught into x minus x naught. This is a linear approximation. So whenever this f dash of x naught, which is the slope, is strictly greater than 0, we get that the linear approximation is increasing. Okay, so whenever the linear approximation is increasing, we can say that the function is actually increasing. That is what you infer from that. That means if this is a function, the corresponding linear approximation at this point will be the line like this. So this line is increasing at this point. That means the function is increasing at this point also. That's the observation we get from there. That is, f dash of x naught is strictly greater than 0 will imply f is increasing at x naught, and f dash of x naught is strictly less than 0 will imply f is decreasing at x naught. So that's the observation you get from there. And also suppose if y is equal to f of x, and suppose you are assuming f dash of x naught is strictly greater than 0, we are going to end up with the definition we mentioned earlier about an increasing function. For that, consider the difference quotient, delta y by delta x. You know it is equal to the fraction sitting here. And when we apply limit delta x tends to 0, this will be equal to f dash of x naught. And we have assumed that to be equal to f dash of x naught is strictly greater than 0. Now you just simply rewrite x naught plus delta x as x. That is x naught plus delta x is equal to x will mean delta x is equal to x minus x naught. We just rewrite what you have here, and you know that that is strictly greater than 0. That means the fraction is having the numerator and denominator. The numerator and denominator should be having the same sign because this is strictly greater than 0. That is either f of x minus f of x naught strictly greater than 0 and x naught minus x minus x naught is strictly greater than 0, or f of x minus f of x naught is strictly less than 0 when x minus x naught is strictly less than 0. So that both the cases will imply x strictly greater than x naught will imply f of x strictly greater than f of x naught, and x strictly less than x naught will imply f of x strictly less than f of x naught. Both are the characteristics of an increasing function. So what we obtained is that whenever f dash of x naught is strictly greater than 0, we are getting that the function is increasing by the definition we mentioned in the earlier phase. So similarly, if f dash of x naught is strictly less than 0, you can say that f is decreasing at x naught. So you also can see the different functions. F of x is equal to x cube, f of x is equal to minus x cube, f of x is equal to x square, and f of x is equal to minus x square, and see how the function is increasing at 0. See here the function is uh, changing sign from negative to positive. Here the function is changing from positive to negative. Here the function is neither increasing nor decreasing. Here also the function is neither increasing nor neither decreasing. So you have to become familiar with these functions and make a good notion about the same. And in the next section, we will be seeing the increasing and decreasing test and the rest of the sections. So thank you for watching. Please do write down the lecture notes and work out the problems. Thank you.